Hi, Brittany. Two people. See, wait. Hi, everybody. I'm waiting for people to come in. I see Sylvia. You're always the first one that pops up. You must have good internet.
I guess so.
Okay, that's a good thing. Let's see what else I got here. How was Easter? Weird. First time I ever attended an Easter service online. People are telling me hello. And it was in West Virginia. Yeah, I can see you now, Alice. See, you got to turn the light on there. Allison, how's the Quest Center stuff going?
It's good. I mean, I haven't had anybody come in yet, but
yeah, I kind of worried that would be the case because I mean we're in such close touch with most people are in such close touch with their instructors. Hopefully, that I wondered if anybody would come in. But anyway, it helps you earn a little money, whatever. Okay, guys, I tell you what. Let me I'm gonna go ahead and share the screen, and I'll let people come in as they will. And we can ask some questions if you have problems with anything. Let's see what I've got here. Okay. Let's see. What I'm putting up here right now is the assignment sheet, the new assignment sheet, and I backed it up through part of last week so we can sort of keep track of where we are, and then we'll just wait for a few minutes for everybody to come in. What I've done here is back it up for where we were talking on Wednesday, since we have Friday off. Okay, let's see. I got lots of people that want to come in. Let me get them in here before I start talking. Okay. I got Damaris. Let's see. I got Tiara. Okay. All right. So, this admit thing is annoying, but I understand why it is being used. Okay. So I backed it up through Wednesday. It has to do with solving homogeneous linear DEs with constant coefficients. I want to make sure everybody's okay on what it takes to do that. We're going to talk about it again today. We did not finish the section, so I thought I sort of sorted through these problems to see if you could do all of them. But one of the things that I'm doing today is what happens when we get complex roots. If one of those snuck in there, we'll just do it later. We'll do it after today, because that's what I'm going to talk about today. The other thing I wanted to point out to you is that on the bottom of this, the next homework that's due is due this coming Friday. It is on this stuff that we're doing right now. Okay, so some of these you should actually be able to do already if you want to start looking at them and so forth, or ask me questions about some of the homework that looks like some of this. So, all right. Let me see one other thing here. I ran it through Wednesday and Friday. It's probably going to take me 2 days to do section 4.4. These sections take a long time to do because they're so dense. They have so much in them. And this handout right here, this class exercise, is something that I'll do, that we'll try to do together in class. It's something I usually pair people up on to work on, but we'll figure something out. The other thing I wanted to point out is this is I put this on Moodle, but I think I posted this after I think I put this on my my whiteboard after I posted it. I made sort of a comment here. You got to solve a system of 3 equations and 3 variables to do this. My suggestion there is that you use your calculator with the matrix app key to enter a matrix and put it in reduced row echelon form, and then use MathFrak so it gives you solutions that are not decimal solutions. Okay, I got people coming in. Okay. So you need to think about whether you know how to solve a system of equations in 3 variables on the calculator, because that definitely would take a lot of time to do that. So is there anybody right now that doesn't remember how to do that? I mean, you put it in a matrix thing, in a matrix, and you hit RREF and it should give you the solutions there. Is there anybody that doesn't remember how to do that? Because I can post a sheet on it if you need me to. Anybody interested in that? Okay. All right.
I am. You can
Okay.
post a sheet.
All right.
I'll take
Here,
it.
I'll put it in there. I'll put the instructions on how to use your calculator to solve a system of equations, because that's what you're going to need to do on this one. You're going to be finding C1, C2, and C3 for some DE, and you're going to be trying to determine those constant coefficients. Okay.
Thank you.
Okay. All right. Good. Okay. So let me go back to what I wanted to start today, and we'll just kind of warm up on a problem. Let's see if I've got it here. Yeah, let's look at this thing. Guys, what we're doing is solving these higher order. We've gotten into higher order now, DEs that are equal to 0. They're always homogeneous. This thing I'm showing you right now is only to solve a homogeneous part, a homogeneous equation, or one that's associated with some non-homogeneous one. We're going to be using it in the next section, so you're going to get a lot of practice doing this. So we learned last time that it had to be of the form e to the mx. All right. So basically, in general, we were looking for some solution of the form e to the mx. And to do that, what we did was we plugged e to the mx in. We put it's easy to find its derivatives, and you can see that you keep getting the m repeated, m to the first, and m squared, and m to the third. And the coefficient equation is easy to see. It's really just, you can look at it here and you say, okay, in the fourth derivative, I'm going to have repeated m 4 times, so it's m to the fourth plus 3m cubed plus 3m squared plus, that should be an m right there. That should be an m right there. Sorry, looks like I got it. That should be an m. Okay. M is associated with the first derivative, m squared is associated with the second derivative, m cubed associated with the third derivative. So that, remember, is called the characteristic equation. I want to solve it. I want to find its roots. And I put one up here as an exercise that made us do several different things. And we've either got to factor it, or we've got to find its roots using some of this synthetic division stuff that we used. And what was called the rational root theorem. So the first thing I did was I pulled out an m here. That means one of the solutions.
Dr. Harrell?
Question.
I think Sarone is waiting to be let in.
Okay, I thought I let her in. Sorry.
You're good. Thank you.
Me. Okay. Can you hear me now? Everybody hear me?
Yes.
Okay, good. All right. So is Sarone in? Okay, Sarone's in. Okay, good. I'm sorry, Sarone. I thought I let you in.
That's okay.
When I pull out an m, I get m equals 0 as one of the roots. I'm left with m cubed out of that one, 3m squared out of that one, 3m out of that one, and a 1 out of that one right there. Okay, so I've got to essentially find those roots. Okay, the roots of that thing right there. Now, what I know from that m equals 0, I'm going to go ahead and sort of start doing what I know, is that one of these, that root being 0 means it's going to be e to the 0x. That's the time, that's a time when, guys, you're going to end up with just a 1 there. You're just going to end up with a C1, okay? Now, the other roots I have to find, okay? So this is something that it doesn't look too easy to factor. It's not easy to factor. You might recognize something about it, but let's just say we were using that rational root theorem. And we looked at these were the p's, plus or minus 1, and the q's were the coefficient on that, plus or minus 1. When I put plus or minus 1 over plus or minus 1, again, that's the p's and that's the q's. And the p's and q's come from their p's, and the coefficient on this are the q's. That tells me that the only possible roots are 1 and minus 1. You check roots by plugging it into this thing. So if we tested 1, you can see 1's not a root. If you test minus 1, you see 1 is a root. Minus 1 is a root. So I'm going to use synthetic division to find out what's left. So ultimately, guys, if minus 1 is a root, and we're going to be using this a lot later, you're going to have a factor of x minus a minus 1. And let's see, that didn't come out too good. And this other thing that's left here, you know you've got a root when you look the last term there is the remainder. You get a 0 there, you've got a root. What this tells me, this thing right here that's left, are the coefficients of the remaining reduced polynomial. So that would be 1m squared plus 2m plus 1, right? When I factor that, and I should not have put an x there because I'm so used to x's, but it's an m for the characteristic equation. So what I get out of that, let me go up here, is m plus 1. And then it looks like if I factor this, it'll be m plus 1. Another m plus 1. Every time I touch that top thing, it goes. Let's try again here. M plus 1 and m plus 1. So, because this thing will factor into m plus 1 times m plus 1. Along with the m that came initially, that's the whole factored form of this characteristic equation right there. So we've got a root of m equals 0. So that's where that part of the solution comes from. Then we've got a repeated root of minus 1. It has multiplicity 3. When that happens, when m is minus 1, it has a multiplicity 3. The way we start to write the solution is like this. We'll have C2 e to the minus 1x. And then what happens with the multiplicity is it steps up and adds an x, e to the minus x. And then the C4 is going to be x squared, e to the minus x. That's one of the last things we did on last Wednesday, which seems like years ago at this point. So that's how that's sort of a review of what we did last week. We could get real roots, we could get real repeated roots, or roots of multiplicity k, whatever. Okay. Is there anybody that's not okay with this one? All right, let me ask, did you have any issues with the homework? Let's start with let's do that. Anybody have any problems with homework on this stuff? Anybody issues with that? They're pretty easy if you figure out how to find the roots and sort of know the form of the solution. Now we're going to be using this in the next several sections. We're always going to have to solve a DE, whether it's homogeneous or linear or non-homogeneous, we're going to have to solve this associated homogeneous thing. All right, seems like somebody else is possibly trying to get in. Let's see. Don't see anybody. Okay. All right. So questions on the homework? Everybody okay? All right. The only thing we have not covered as far as roots go is what happens when you get a complex root. All right. I've got a gallery view here. Is there anybody in complex analysis right now? Raise your hand if you're in complex analysis, right? Okay, Saron's in there, and I can't see Damaris, but I don't think you're in there. Brittany, are you in complex analysis, Brittany?
I am.
Okay.
I am
All right. And Tiara, you're in there too? Okay.
Yes.
So you guys are going to find some of this familiar, I hope, and it might help you guys out. And it's not terribly hard to talk about to everybody else. So I'm going to be doing a little bit of complex analysis in this part. Now, what I mean by complex roots is this. If I have a characteristic equation like this associated with this homogeneous equation with constant coefficients, it'll be m squared plus n plus 1. I can't factor that. And as a matter of fact, I need to use the quadratic formula on it. And so it'll be coefficient here -1 plus or minus the square root of 1 squared minus 4ac all over 2a. That ends up being -1 plus or minus the square root of -3 all over 2. And the square root of -3, I'll probably keep pointing this out here, guys, but the square, just the definition, the square root of -1 is defined to be I. So the square root, for example, of -3 would be I square root 3. Writing that as 1 times -3 or -1 times 3 and just splitting up the radical. So that's what happens when we have a square root under a square root of a negative number. Now, one thing I want to point out here, what's under here, that thing under the radical there, the b squared minus 4ac, these complex roots are going to happen when you get a negative under the radical. So that thing's called the discriminant, and essentially it's called that because it discriminates between the kind of roots you've got. If that thing were 0, I'd have repeated roots. If that thing were non-zero and positive, I'd have 2 real roots. Okay, but that's sort of the way it goes. Now, one other thing I want to point out here, because it becomes important today, is that these roots come in what we call conjugate pairs. There's a -1 plus I root 3 over 2 and a -1 minus I root 3 over 2. Okay, so they come in a pair. Now, how do we write the solution of the DE then if we get these complex roots? It turns out that it really is the same way, but we're going to write it a lot differently depending on some things that happen with complex numbers. So normally I would say these are 2 distinct roots. We got a plus there, we got a minus there. So we'd write e to the m1, there's the root right there, -1/2 x. All right, and we've got plus c2 times e to the -1/2 minus I root 3 over 2x. Now, it's sort of the same as distinct roots. It's e to whatever times x. But we don't write it like that at all. We've got a little work to do before we can figure out how we write it. But one thing you will see here is if I sort of break this power down, it'll be e to the -1/2 x times e to the root 3 over 2I times x. And breaking this one down, it's e to the -1/2 x minus I root 3 over 2x right there. And what you can see there is that we could, if we wanted to, pull this e to the -1/2 x out of both of them, and you'd be left with c1 e to the root 3 over 2I x plus c2 e to the minus root 3 over 2I x. Usually we put the I in front of the radical. I don't know why I did that like that a minute ago. But that's a 3 under there. Okay, so the question that we've got to answer here is, do we leave it like that? And the answer is no. There's something in complex variables that allows me to rewrite this in terms of 2 functions that I'm better able to deal with. Okay, questions, anybody so far? All right, so let's look at something here. There is a very famous formula from a very famous mathematician in mathematics that's called Euler's formula. Euler is known as the prince of mathematicians. No, that was Gauss. Euler, sorry, I started to say the prince of mathematicians, but he's one of the most famous historically mathematicians of all time. There is a formula that Euler came up with that says e to the I theta equal cosine theta plus I sine theta. Now, you got to wonder how in the world that happens, okay? It is a very important formula. I know everybody that's taken complex tyranny, so Tierra, Cerrone, Brittany have seen this. It also leads to lots of tattoos, and my explanation of that is this. The tattoo that a lot of mathematicians like to carry around in various places, hidden or not, is this thing right here. E to the I pi equal -1. If you were to plug pi into this thing right here, the cosine of pi is -1. The sine of pi is 0. So you get this kind of funky thing here that's an e, which is irrational, a pi, which is irrational, I, which is an imaginary number, and you come out with -1. That's just like, wow, what happened there? Okay. The reason I talk about tattoos is I know more than one mathematician that has this as a tattoo. I know one guy that has it on his wrist. Somebody else has it, on his neck, whatever. Anyway, this is a big thing in mathematics. A lot of people like that. That's an amazing thing happening there. All right, now let's talk about how we get it. Now, the next thing I want to know is how many people have had series yet. Now, you would have either had it in Calc 2, the end of Calc 2, or the beginning of Calc. There used to be a Calc 3. There used to be a Calc 4, so it used to be in Calc 3. But if you've had Calc 3 and 4 or Calc 3, raise your hand here. Let me see. Who's had a calculus course after Calc 2? Okay, we got Sylvia, Saron's had it. Ella hasn't. Tierra has. Brittany, have you had it?
No.
Okay. All right. So we got Saron, Tierra. Damaris, have you hadn't had Calc 3, have you?
I have not.
Okay. You had Calc 2. You had Calc 2. So you probably had it at the end of Calc 2 because you took Calc 2 recently, I think. And Allison, you've had it? You had Calc 3, 2 and 3? Definitely 2. Okay. All right. So let's look at this for a minute. And even if you haven't, you can learn a little something here. In the end of Calc 2 and used to be the beginning of Calc 3, we talked about something called infinite series. And an infinite series was an interesting way to write a function in terms of a polynomial function, which does what we call converges to that function. Now, the notation, let's just look at it real quickly. This is a summation notation. It says you're going to start plugging in n's and you're going to go to infinity. And for instance, if I plug in a 0 here, my first term in this series will be x to the 0 or 1 over 0 factorial. And that's 1. If I plug in 1, I get x to the first over 1 factorial. If I plug in 2, I'll get x squared over 2 factorial, which is just 2. And so on. If I plug in 3, it'll be x cubed plus 3 factorial, and so on. So what happens here is this. You can go out to infinity with this. And what happens is the further out you go in this series, the more it approximates a value for e to the x. So for example, if I said e to the 0.23, if I wanted to find an approximation for that, it would be approximately 1. I would plug in everywhere there's the x right here. I'm going to plug in 0.23. So I have 1 plus 0.23 plus 0.23 squared over 2 plus 0.23 cubed over 3 factorial, and so on. And the further you go out in there, in other words, the more terms you look at, the closer it gets to the value of e to the 2.33. Now that's an irrational number, so you're getting more and more, it's getting accurate to more and more decimal places. So that's what we call an infinite series representation for this e to the x. Now, an interesting thing happens here. if I say, let's plug in e to the ix, let's find out what e to the ix is. So in that series, instead of where I put 0.23 a minute ago, I'm going to put ix. So it'll be 1 plus I, in place of x, I'll put ix. In the place of x squared, I'll put ix squared, or ix and then square it. I'll put ix and then cube it. I'll put ix to the 4th, and then 4th factorial, and ix to the 5th, and then 5 factorial, and so on. Now, I think probably everybody has had this in high school, but let me skip over to right here for just a second and talk to you about the powers of I. I think in high school, when you do the quadratic formula, this might be where you do imaginary numbers, because you do get these negatives under radical. So it gives high school teachers a little bit of a chance to talk about what an imaginary number is and how it behaves. So remember that I is the square root of -1. And that means I is the square root of -1. So I to the first is just I. But if you look at I squared, for instance, if you said I squared there, it'd be the square root of -1 times the square root of -1, which is just the square root of 1, which is 1. So if you square I, you simply get -1. Oops, it's the square root of, yeah, you square, I'm sorry, I did that. I messed that up. Let me do this back. If you square something, you get what's under the radical there. So what you'll end up with, you don't want to multiply that right there. What you'll end up with is I squared is -1. So you're undoing that thing right there, and you get -1. If I squared is -1, then I cubed is just I squared times I, and that'll be -1 times I, and that's -I. I to the 4th is just I squared times I squared, and that's -1 times -1 equal 1. Now, those of you who, and anybody that might be familiar with this, what would I to the 5th be? What would I to the 5th be, guys? Let's try to do it in terms of something we've already had. For instance, well, anybody might know what I to the 5th would be? Anybody got a guess about what I would 5th would be, or knows?
I.
Yeah, it's I. So see, Tara says I, and she's right. Because you've got I to the 4th times I, and we just found out that I to the 4th was 1. So 1 times I is I. Now, what you see here in these things is that it starts to repeat again. I to the 6th would just be I squared, which would be -1. So it repeats I, -1, minus I, 1, then it starts again. I to the 6th would be -I, and so on, okay? So, so what we want, not minus, I don't know what I'm looking at here, I'm looking at the wrong thing. I to the 6th would be I to the 4th times I squared, which would just be -1. Okay, so it starts to repeats in groups of 4. So what I'm gonna do with this right here, this this thing that's got these i's in it, is just raise all those i's to their powers, and find out what we've got. And what I've got here, I'll move that up there. What I've got here is that this, if I square these things out and look down here, I'll have 1 plus ix. I squared was -1, so that gives me a minus right there. So that's x squared over 2. I cubed was -I, so that gives me -I x cubed. I to the 4th was 1, so that gives me 1x to the 4th over 4. I to the 5th we saw was just I, so we get I x to the 5th plus 5, and so on. Now, that, you wouldn't think that would be a big deal, but just like with e to the x, there are power series representations of sine and cosine. So what I'm going to do now is group all the ones that don't have an I in them. This one, that one, and so on, and put those together. And then I'm going to group the ones that have an I in them. So that one, that one, that one right there, and pull the I out of it. Now, it turns out that this thing right here is the series representation for cosine x. In other words, if I wanted to find cosine of 0.1, I could find an approximation of that and a better and better approximation if I went further out in the series and put in 0.1 for x. Polynomials are always easier to compute than functions like this. So, so that's what we would get there. This one right here, this thing right here is the series representation for sine, okay? So what that says is e to the ix, remember that's what I was plugging in to begin with, is cosine x plus I sine x. And that's Euler's formula, okay? Big formula. And I know that those of you in complex have looked at that. It's one of the first things you look at when you get in complex. Okay, all right. So that's, you may or may not have had that before, but if you take another calculus course, you'll see that, or maybe you had it at the end of Calc 2. Okay, now, what's that got to do with what we're trying to do? Well, what we're trying to do is this. We had, a minute ago, we had some complex roots that look like this, -1/2 minus I root 3 over 2. They're the complex roots there. What I want to, and we looked at, we said we could pull out the e to the -1/2 x, but, and this was, we had plus or minus, those are the two roots we had, but we were left with e, we had a C1 on this maybe, to the I root 3 over 2 x, and we had a C2 e to the I minus root 3 over 2x. And what we're trying to do is rewrite these things. And we want to rewrite it using Euler's formula. So in the end, guys, what we want is to have something with sine and cosine instead of this weird thing like right here that Euler made a nice form out of. Right, this is square root of 3 right here, okay? All right, so here's the goal. And I'll do it generically first, and then we'll talk about what we're going to do. Question anybody about anything so far? Okay, I know I pulled some new stuff on some of you, but it's just a way to get to here so I don't just magically say, well, it works like this. So suppose we have complex solutions. In other words, we have maybe alpha plus or minus beta I. In that problem I did before, the alpha was -1/2, the beta was root 3 over 2. Now, alpha is called the real part. It's a hard time writing this morning at all. Alpha is called the real part of that complex number, and beta is called the imaginary part because that's where the I is. So the imaginary part. So I want to see what these solutions really look like if I use Euler's formula. So generically, they look like that. So if I write it as e to the x and that to the x, those were you can show those are linearly independent. I'm going to get you to do that a little later on when I change its form. It would be C1 times this one, notice is alpha plus I beta x. And this one is C2, that's alpha x minus I beta x if I add the powers. I want to separate out this e to the alpha x. I'm going to pull it out because I can write that. That's easy to write. Alpha is just the real part. What I'm trying to do then is rewrite these two pieces using Euler's formula. Okay, so that's what I'm getting ready to do. I'm getting ready to use Euler's formula and see if we can some way figure out what's left out of this thing to be the solution, a different way of looking at the solution. Okay, so guys, just watch me here. You can write this down if you want to. Some of this is in the book. I added a little bit to it, but just try to follow me, and I'll try to leave you a little time to write it if you want to write it. What I'm going to do with the e to the I beta here is use Euler's formula. So it's the cosine of beta x plus I times the sine of beta x. When I have e to the minus I beta x, it'll be cosine of minus beta x plus I sine of minus beta x. Okay. So we take whatever the angle is. It was that e to the I theta equals cosine theta plus I sine theta. My theta in this case is beta. My theta in this case is minus beta. So that's what I'm putting in for that thing right there. Now, there's a little bit of trig involved here that's going to actually help us out. There's a formula in trig that you guys hopefully all know, that the cosine of minus x is the same as the cosine of x. Okay. There's also in the same, they're called the formulas for negatives, guys. If you look in your calculus book, you'll see these things as the formulas for negatives. The sine of minus x, on the other hand, is minus the sine of x. So there are reasons why this works. You can look on the unit circle and see easily why it works. But so when you take the cosine of minus x minus an angle, it's the same as taking the cosine of the angle. All right. That's because it's reflected across the x-axis. Okay. And in 1 and 2, cosine's positive. In 3 and 4, cosine's negative. So it'll be the same. With sine, you're reflecting across the y-axis. So the sine of minus x is actually the opposite of sine x. If you look at the unit circle, you could see some of these things. So the sine of minus 30 degrees is minus the sine of 30 degrees. Okay, so I'm going to use that trig formula right here. I'm going to say, well, the cosine of minus beta x is the same thing as the cosine of beta x. So that's using that formula right there. The sine of minus beta x, the sine pulls through, and it ends up being minus I sine beta x. Okay. Now, so I just threw those things right here into Euler's formula and came up with something like this. Now, notice here, and this is where I'm going to try to sort out what's independent in this mess that I've got in front of me here. Notice I'm gonna say, well, let's see if we can. This thing's true for all values of C1 and C2. All right. If you don't have any conditions on it, that's the generic form of it. So let's just let briefly C1 equal C2 equal 1. So in other words, for right now, let's let this be 1 and that be 1. Okay. If I let both of those be 1, notice that you'll get cosine beta x twice. All right. But the I sine beta x and the minus I sine beta x are going to drop out. So in the end, what you have, if you let C1 equal C2 equal 1, is the e to the alpha x that you already had, and this 2 cosine beta x. So that's what happens if I say, okay, let's see what happens if the sign drops out. I'm going to drop the 2 here, guys, because the 2 is just a C1 or a C2. I mean, whatever. That's going to get absorbed into some C, and sort of the basic part of that is e to the alpha x cosine beta x. So that's sort of what I soak out of it if I make the signs drop out. Okay. Now what I'm going to do, and I know that's just an easy way to get at what's really important in this equation. The next thing that I'm going to do is I'm going to let's get rid of the 1 and the 1. I'm going to let C1 equal 1, all right, and C2 equal minus 1. Can everybody see that? I got it down a little low here. Let's do that. Okay, get rid of that. So I'm going to let this be 1 and that be minus 1. Well, if I let that happen, the cosines drop out, and minus a minus here gives me plus I sine beta x. And I've got another I sine beta x to add it to here. So what I end up with is 2I sine beta x, of course, with the e to the alpha x that goes there. Now, the basic part of this, if you think about that as just sort of a constant, and 2I is a constant, it happens to be a complex constant. But the important part of that is this. All right, so we have got actually what we need. Let me come up a little bit and ask a couple of, and state sort of what I've found here. What we see is that we can rewrite all of this stuff with the e to the minus, or e to the I theta, in terms of sines and cosines. It says that our solution is going to look like this. C1, e to the alpha x cosine beta x, C2, e to the alpha x sine beta x. That actually, guys, is going to be the general solution here. All right, the general solution when it involves complex roots. And I want you to look at the form. And by the way, I could pull the e to the x out of that, but let me write it. Let me pull it. I probably pulled it out a little bit further down here. Yeah, I'm just going to go ahead and write it. So I could pull the e to the alpha x out, and I wind up with this C1 cosine beta x plus C2 sine beta x. Now, that's the general form for those two roots on that homogeneous linear DE. Okay, so why don't you look at the form? This alpha was the real part of the root that we found. Remember when we found those roots were minus 1/2 plus or minus root 3 over 2i? The alpha was the real part. That's what's going to go right there. Okay, I'll write this one out in a minute. The beta, without the signs, is what's going to go there. So the 1/2 or the minus 1/2 would go in here, and the minus root 3, I mean just the root 3 over 2 would go in for beta. Now, I went ahead and wrote that down a little further down. Right here, it says where alpha is the real part and beta is the imaginary part. Okay. Now, here's something. Let's just finish up this problem that I started, and then I have a couple of words to say about what this thing looks like. Do I need a question? Anybody? Does anybody want to see the last screen or want to scroll back down or anything? Okay. Give you a little time to breathe here. So that's what it looks like. We began this lecture with y double prime plus y prime plus y. We found out that the roots of the characteristic equation were minus 1/2 plus or minus I root 3 over 2. So that means alpha is, and I should, there, that didn't belong there. Alpha's actually just minus 1/2. Okay. So alpha's minus 1/2, and beta's root 3 over 2. So what the general solution looks like is C1 e to the minus 1/2 x cosine root 3 over 2x plus C2 e to the minus 1/2 x sine root 3 over 2x. And if you're wondering about the plus or minus there, that all gets absorbed into the Euler's formula thing. So that's the minus one goes with the sign because, well, the root 3 over 2 goes with the sign. You just use root 3 over 2. You don't use the plus or minus there, just the root 3 over 2. So that's what that solution for that thing looks like. Often, as I said before, we'll pull out the e to the minus 1x. All right. Now, one thing you want to, a couple things, let's just look at a couple of things while we're here. And then we'll do numerous examples, okay? If these really are the solutions to this second order equation, which they are both linearly independent and they're both solutions. They're linearly independent and are both solutions. Remember, in order to have a general solution, we needed a fundamental set. So these things right here form a fundamental set. And there are two of them because it's order 2. and they should satisfy the DE, both of them. And you can't write one in terms of the other one. They're linearly independent, but I'm gonna give you a bonus problem that'll convince you of this, I hope. How do we usually show things are linearly independent, guys? How do we usually show two functions are linearly independent? What do we use? Anybody? What do we use that we learned in, I guess that was that long section 4.1. What was it called? I'm gonna wait out my wait time here. What was it called?
Is it the Wronskian?
It's the Wronskian. Exactly. It's the Wronskian. So that's what I'm gonna do to show these things are linearly independent. So I'm gonna start with and I don't expect you to write this one down, guys. This was messy. And it doesn't even look like it's gonna work when you first do it. But remember, there was a homework back there where we were trying to show something was a fundamental set. We needed two of them for a second order. We needed both of them to satisfy the equation, and we needed them to be linearly independent. So in this one, I just said, well, I'm just going to play around with this thing and make sure that it really is a solution. Now, remember, there was the DE. So I'd need a Y. I need a Y prime, and I need a Y double prime. Now, you can see, here's why this thing turned out to be such a mess, guys. Initially, you have to use the product rule. And then you get two more things you have to use the product rule on to get the second derivative. So you're generating all these different pieces of things. So that was right there. That was just me trying to be really careful finding the derivatives. Okay, so Y prime and Y double prime, so I could plug it into this. I really don't, you probably just want to watch me here, because I mean, you can do it on your own and make sure, or you can try the other one. You can do the one that's got sine root 3 over 2x in it and show that it satisfies it. But let me just show you what happened. What I do, of course, is take the Y double prime and plug it in to the equation. So the Y double prime was, I think it was all of this. The Y prime was that. And there was no, that's part of Y prime. Anyway, that's why this is such a big mess. All right, Y prime plus Y. The Y was in there somewhere. But anyway, what happened is that I looked through to the things I could combine. I could combine this. The ones I've got a check on, I combined. The ones I've got an X on, I combined. And it turns out they all drop out. Okay, you can verify that. But they did turn out. When I looked at it to begin with, I was like, oh, I made a mistake, because it didn't look like anything was going to drop out, but it does drop out. Okay, so we end up with 0. Okay, so that's one thing we could do. We could check to see both are solutions, and they are. Now, here's a bonus for homework. Now, let me talk to you guys about how I'm doing these bonus points, because some of you got bonus points on the last homework. If I say on your, there were 5 bonus points on the last set of homework, and there was only 2 credit points. So you could get a 2 out of a 2 if you just did the credit points. If you got the 5 extra points, that means I'm going to give you a 7 over 2, which means that 5 other points, probably, you want to look at it this way, can be distributed over some homework where you didn't get all the points. What I'll do in the end with the homework is add up how many problems we actually assigned, okay, or how many points I actually assigned in homework problems, and then add up the points you got, and then get a percentage there. It'll count as a test grade. So if you get these bonus points, it just adds things maybe that you might have missed before. So if you got 5 bonus points, you missed 5 on the previous homework, now you're even. You got 100% on both of them. Okay, so so if you can, it's really to your benefit to try to use these to get these bonus points. So this one shouldn't be that hard, because it's messy, but it's not hard. And I'm going to give 3 bonus points for it. Okay, and it is to show that these 2 things right here are linearly independent. And I want that before class on Wednesday. Okay, it really shouldn't just do it first up. It really shouldn't take you very long. You're going to put it in the Wronskian and do what you do with a Wronskian. So those are my Y1 and Y2 solutions that I'm trying to show are linearly independent. And the answer somebody gave a second ago about you use the Wronskian is the answer to the question. Okay, so that one shouldn't be too bad. Obviously, you're gonna have to use some product rules and so forth, but it's not too bad. Okay, so that'll be +3. Okay. Question anybody about that? Now I'm going to start working. I'm going to sort of state my conclusions here, and I'm going to start working problems. Not only problems with complex roots, but problems with all other kinds of roots, distinct roots, repeated roots. I do have one more thing to add to this, and it has to do with what if you get a repeated complex root. I'll talk about that in just a second. All right, so let me go up here. So the conclusion we've got here, guys, is this. Complex roots come in pairs, alpha plus or minus I beta, and they'll be solutions or roots of the characteristic equation. So the solution to the DE whose characteristic equation has this pair of roots is that thing right there. E to the alpha x, real part, plus C1 cosine beta x, imaginary part, plus C2 sine beta x, imaginary part. There is no I in here, guys. The C2 takes care of whatever constant that would be there, whether it's real or imaginary. Okay, so that's what we just spent, however long we spent on it. I don't even know what time it is. Let me see, 10:22. Okay, so let's just do some examples. Everybody, that's important. That's the upshot of everything I just did. All right, we'll move it. Speak now or forever hold your peace. Has everybody got it? Okay. So let's do a problem. Okay, I've got 3y double prime plus 3y triple prime plus 5y double prime plus 10y prime minus 4y. Okay, minus 4y. I write the characteristic equation, 3m cubed plus 5m squared plus 10m, the first derivative, and the function y just leaves me with a 4 right there. So it's a cubic, not easily factored. So I need something to hang on to here. I need to get a root. So let's go over that rational root theorem again. There's a little blurb on this in your book towards the end of this section, I think, and it references the rational root theorem. But it's how we're going to just get a handle on what some root might be. So remember that the factors of -4 are my p's. So plus or minus 1 and plus or minus 4. These are the factors of that 3, all right, are my q's. All right, so plus or minus 1 and plus or minus 3. And my possible rational roots are all the possible p's over q's. So this over this over this. So plus or minus 1 over plus or minus 1 gives me 1 and minus 1. Plus or minus 4 over plus or minus 1 gives me 4 and minus 4. And then I'll get here plus or minus 1 over plus or minus 3. And plus or minus 4 over plus or minus 3. So I'm just, without further ado, I'm going to do this already, just tell you that if you tested these, and that's what you do to get a handle on the first root, plug these things into the characteristic equation, and anything that gives you 0 is a root. So that what I get here is 1/3 is the one that worked. None of these whole ones will work. I always check the whole ones first because they're easier to check, but none of them worked. That's a true statement. Yeah, none of them worked. So it's either plus or minus 1/3, plus or minus 4/3. Turns out to be 1/3. Now, if 1/3 is a root, m minus 1/3 is a factor. And what I want to do is find out how what's left when I plug in. It's a factor of this thing. What's left when I do the synthetic division? In other words, what's left when I divide this thing right here by m minus 1/3. We're going to use synthetic division again to sort of find out what's going on here. We'll do the division, and I need to cut that landline off. I'm gonna save money and annoyance. So what I'll do is I'll put the 1/3 right there. I put the coefficients 3, 5, 10, and -4. Remember what I did with the synthetic division? I brought down the 3. 1/3 times 3 is 1. Put it there. Add here is 6. 1/3 times 6 is 2. 10 and 2 is 12. 1/3 times 12 is 4. -4 plus 4 is 0. That 0 is what I'm looking for. Okay. So the reduced polynomial has its coefficients right there. So it's 3m squared plus 6m plus 12. Now, guys, I'm going to pull a 3 out of that. And what I'm left with is m squared plus 2m plus 4. I can't factor that. As a matter of fact, if you look at the discriminant, b squared would be 4 minus 4ac would be minus 16. I've got a negative under the radical in the quadratic formula. So I'll use the quadratic formula on that thing. I wind up with this thing, -2 plus or minus the square root of -12, which of course, that's 4 times 3, so I can pull out a 2. It's a negative, so I've got the I. It's -2 plus or minus 2i root 3. Carry it all the way down. Do not make the freshman mistake of canceling these and not worrying about that. Please don't do that, all right? That'll be -1 and then plus or minus 1i root 3. So what we've got, using the quadratic formula, is that thing right there, where that is alpha and root 3 is beta. So here's what my solution looks like. The alpha is well, let's look at the whole solution. One thing we had was that we knew that m equal 1/3 was one of the roots. That's a real root. So the part of the general solution that goes with that is c1 e to the 1/3 x. Okay? The part that goes with these two imaginary roots, alpha was -1. So I've got the e to the -1x. That's what goes there. Where the root 3 goes is with this c2 cosine root 3x plus c3 sine root 3x. I wrote the two together there. I will often pull the e to the -x out. But if you were doing, if you were trying to find some solutions that had conditions with them, you might want to leave it like this, because you're going to be trying to find C1, C2, C3 there. Anyway, that's what it looks like. Question anybody about that one? All right. Let me make a quick note about higher multiplicity complex roots. What I mean by a higher multiplicity root is a complex root that's repeated, and I'll give you kind of an example of that in a second. But they work really just like the other ones we did. Remember when we had repeated real roots? If I had a e to the mx and it was repeated, I would put an x e to the mx. If it were repeated twice, I'd put an x squared e to the mx, and so on, depending on how many times it was repeated. The same thing happens with complex roots. If you just have one set of complex roots, one conjugate pair, it looks like what we just talked about. E to the, say, 1x plus, if I were looking at roots that were like one, that would have been a 1 plus 2i root right there. 1 plus or minus 2i. If somehow that root got repeated, because see, there's the alpha's 1 and the beta's 2. Okay, right there. If that got repeated, and I'll show you in a second how it can get repeated, you'll just put an x on the next one. Same thing, put an x. If it got repeated 3 sets of times, you'd have an x squared. It works exactly the same. So I've got an example for you down there of that, down here. So let's go up a little ways. Suppose I had this one. I'll just leave that up there. Suppose I had y, the fourth derivative of y, plus 8y double prime, plus 16y equals 0. The characteristic of the equation here is m to the fourth, plus 8m squared, plus 16. If I factored that, I'd get m squared plus 4 twice. That's complex roots of multiplicity 2. If I solve one of them, if I solve find out what the roots are, that would be m squared equal minus 4. I didn't necessarily need to go through the quadratic formula. I could have just taken plus or minus the square root of minus 4, which would have been plus or minus 2i. Okay, so plus or minus 2i has a real part of 0 and that imaginary part of 2 right there. So when I write this solution, the first one, I'm going to pull out the alpha here. That's going to be c1 e to the 0x because alpha is 0. And then it'll be cosine of the imaginary part, 2x plus I sine 2x. Because it's repeated, it'll look exactly the same, except it'll have another x in it. If it had been repeated 3 times, I would have had another one like this with an x squared in it. So if I were to write this out in its form here, I'd have c1 cosine 2x plus sine 2x. All right, because the e to the 0x is just 1, plus the c2x, plus the c2x, again, because e to the 0x is just 1, I've just got the x left there, cosine 2x plus sine 2x. Okay. Is everybody okay with that? Okay. Suppose there were some homework problems like this one. So I want to show you what we would do with a problem where we're given this fundamental solution and we want to know where it came from. So I call it going backwards, because usually we're given the DE, asked to find a characteristic equation and then find the general solution. Now we're given the general solution, we got to go back. Okay, so what are the roots here? What are we want to first find the characteristic equation here. So find the characteristic equation. If I find that, I can get the equation easily. Okay. So we look for the roots, literally. Here is one that was a real root. Remember e to the mx? So one of the roots, we'll call it m1, is minus 3. Okay. Now let's look at the second piece here. That clearly came from a complex root. And those complex roots, the next part of this, I'm just going to say m2 whatever. What will the real part of this be, guys? What will the alpha be on this one? Anybody? What will the alpha be on this one? So anybody? Alpha, remember, was the thing we put on the e to the blank thing. What's the alpha there?
4.
4. Okay. What's the beta?
5.
Beta's 5. So what I've got is 4 plus or minus 5i. So ultimately, my roots are, and I say m2, but in this one right here, there are actually 2 roots involved. So I would have, if something's a root, then we could write it like this: m minus a minus 3, and then m minus 4 plus 5i. All right, and then m minus 4 minus 5i. Okay, so that's what that characteristic equation right there has to look like. Because if all of those are roots, then m minus those roots are factors. All right, did I get that written right? That's fine. Now, notice this is going to be an m cubed thing. I mean, I'm not there yet. It's going to be m cubed because I got 3 m's. It's not as bad as it looks, but I do need to multiply it out. All right, I do need to multiply the thing out. So this will be, let me just easily try that here. There'll be m plus 3. Because these are conjugate pairs, these things right here. Some nice things happen there, but I've got to start, I've literally got to start multiplying the thing out. So that'll be m squared times that piece, and then minus m times 4 minus 5i. Don't let me make a mistake here, guys. I left it blank, but get rid of that. 2. Okay, so m minus m times 4 minus 5i. The next one will be minus m times 4 plus 5i. And then the last one will be this one times that one, which will be plus. Notice it's like multiplying the difference of 2 squares. So I'm going to, 4 times 4 is 16. The inner and the outer terms drop out. This times this gives me minus 25i squared. But because I squared is minus 1, that's going to be plus 25. Now I'm going to double check this here, guys. I've got this. I've got m squared from m times m. I've got m times minus 4 minus 5i. This will be minus 4 plus 5i times m. This minus a minus is plus. I'll get 16 minus 25i squared, which is plus 25. Okay, so I get m plus 3 times m squared minus 4m plus 5im. Yell if I make a mistake, please. Okay, minus 4m plus 5im minus 4m minus 5mi plus 41. So this drops out. I get m plus 3, m squared, minus 4m is minus 8m, plus 41. Have I got everything? I think I do. Okay, plus 41. All right, the last thing I've got to do is just multiply. I do need to find the equation. That's what they're asking me to do. So I'm going to multiply this thing out. See what I get? It's a little messy, but m times m squared is m cubed minus 8m squared minus 8m squared plus 41m plus 3m squared minus 24m. And 3 times 41 is 123. No, 123 times 4, yeah, 123. Guys, that's my characteristic equation. If I didn't make a mistake, that's my characteristic equation. Are we okay with that? Let's see, m cubed minus 8m squared plus 41m, 3m squared minus 24m plus 123. So the DE looks like this. Y triple prime minus 8y double prime plus 41. Shoot, you know what I didn't do? I didn't combine my terms. Hang on. Let me do a little more combining before I write it. I can combine the m squares. M cubed, but you see what I was getting ready to do here. M cubed minus 5m squared. So that's gone and that's gone. 41m minus 24 is 17m, I believe. Plus 123. There we go. I just made this one up, so I have no idea what it was going to be. So here's the DE. Y triple prime minus 5y double prime plus 17y prime plus 123y equals 0. Okay. So if you're asked to go backwards, and at least one of the homework problems is ask you to go backwards. So look over that if you didn't get it last night on that one, and now you've got the complex root thing to deal with. One other quick thing here. If you have problems with the conditions, they're no different than what you ever do. You find the characteristic equation, you write the solution, and then if they give you conditions, you plug in those conditions. So if you found your y from this, which that's easy to see because it's a repeated root of 1. So you get C1 e to the 1x, C2x e to the 1x because it's repeated. If you take the derivative, you'll get this. If you plug in 0 to this equation right here, you should get 0. Well, you can see pretty clearly that you would get C1 plus C2. Out of this one, you get C1 plus C2 equal 5, or equal, or plug in 0 here. I get C1 plus C2 equals 0. So C1, I'm sorry, plug in 0, you'll get 5. Okay. So I just put in 0 here and 5 there. In the first derivative, put in 0 here. That's going to make that term completely drop out. You get C1 plus C2 equal 10. I've done something wrong, guys. I have 0. Let me look at my conditions again. I think anyway, you're going to plug them in. I think I might have written one of those conditions wrong. If I plug in 0, oh, I know what I did wrong. Here we go. If I plug in 0 to this one, it's going to drop out because it's got an x in it. So I get C1 equal 5. That's where I got that. Okay, because that dropped out. This is 0. It equaled 5. And then when I found the first derivative and plugged in 0, that became a C1 because of the e to the 0. That dropped out. That became a C1 because of the e to, or C2 because of the e to the 0. So I get this one. Coupled with the fact that C1 is 5, that tells me C2 is also 5. Plugging it in here, and there's my solution. So if you've got initial conditions, they work exactly the same. You take the derivatives, you plug in your conditions. Okay, I have put this on Moodle. It's on the assignment sheet that I showed you right at the beginning of class. There's homework due on Friday. It's homework I made up and put on the sheet, on the assignment sheet on Moodle, so look at that. But what this will do right here is get you some more homework practice. Now you can deal with complex roots. Okay, so that kind of takes care of that. We're going to be using all of this when we go on Wednesday to do non-homogeneous things. So make sure you got a good handle on how to write these things, and they look exactly like they look in the back of the book when you get the answer. That'll tell you if you got the right, if you solved the characteristic equation right, if you did your synthetic division right, all of that stuff. Okay, anybody have any questions? All right, feel free to email me if you have questions. I will put this up on, I'll put this, I hope it's recording. It better be recording. I'll put this up on Moodle, the video, and we'll come back and look at it again. Okay. Why I'm getting a managed participants right here. Okay, that's because I think somebody left. Okay. Oh, Tiara's waiting to get back in. She must have got bumped. Okay. All right. Anyway, guys, I'll put all this up. Feel free to email me if you have a general question or anything I can help you with. And I'll see you on Wednesday. Talk to you later. Bye-bye.
Bye.
Sorry, I got kicked out.
It's all right, Tiara. All I was saying was email me if you have a problem. And just look at the Moodle sheet. Look at the sheet on Moodle for your assignment, okay? All right. See y'all later.
Yes, ma'am.
Okay.